Hello chemistry students, Dr. Tellis here. This next section we are looking at integrated rate laws. It's important for chemists to know how long a reaction must proceed to reach a predetermined concentration for some reactant or product, or what the reactant and product concentrations will be after some time has elapsed. We need a mathematical equation that relates time and concentration. We could then calculate the concentration at any given time, or we can calculate the length of time needed for a given amount of reactant to react. A rate law simply tells you how the rate of a reaction changes as reactant concentrations change. A more useful mathematical relationship would show how a reactant concentration changes over a period of time. Using calculus, we can transform a rate law into a mathematical relationship between concentration and time. This provides a graphical method for determining rate laws. Let's look at our first order integrated rate law. We already covered this. We know that the rate law for first order is rate is equal to K times the concentration of A. And there is a 1 right there that's implied. So this is a first order reaction. Well, using calculus, and you don't need to know the reasoning behind this, but we're able to get the following equation, and this is our integrated first order rate law right here. And on your kinetics formula cheat sheet, I'll show you, I wrote it down for you here as well. Here is your rate law for first order reaction where I have A is my reactants converting into B. So I show that rate is equal to our rate constant times A, the concentration of A. Our integrated rate law is this, or we can rearrange the equation into a y equals mx plus b format. Let's look at what these variables mean. Concentration of A sub t stands for the concentration of a reactant A at time t. That might be after 20 seconds or 2 hours, but whatever that time is, that's the concentration of that reactant after a certain amount of time. Concentration of A sub 0 is our initial concentration. Sometimes I like to think of it as my original concentration of that reactant. The ratio of A sub t after time t over the original is the fraction of A remaining at time t. ln is our natural log, and our units for K is the inverse of time. Let's do a practice problem using our integrated rate law. In the past, cyclopropane was used in a mixture with oxygen as an anesthetic. This practice has almost ceased today because the compound is flammable. When heated, cyclopropane rearranges to propene in a first order process, so we're told it's a first order. If the initial concentration of cyclopropane is 0.05 molarity, how much time in hours must elapse for its concentration to drop to 0.01 molarity? Let's look at what we know. I'm given K. I'm given our original concentration of 0.050 moles per liter. And after a certain amount of time, the concentration is dropped to 0.01 moles per liter. Using our first order integrated rate law, I'm going to plug in that concentration at time t, that 0.01 molar, divided by the 0.05 is equal to negative kt. We were given our k. So 0.01 divided by 0.05 gave me 0.2. The natural log of 0.2 divided by, and so I divided both sides by that negative k to get t by itself. Natural log of 0.2 divided by negative 2.42, and let's double check this and make sure that you're plugging it in correctly. 0.01 divided by 0.05 gave us 0.2. Then I took the natural log of 0.2, and when I divided both sides by negative k, negative 2.42, I got my 0.665, and we wanted 3 sig figs for our final answer. Let's set another one up. Sucrose, a sugar, decomposes an acid solution to give glucose and fructose. The reaction is first order in sucrose, and the rate constant at 25 degrees is 0.21 inverse hours. So we're given K. If the initial concentration is this, so we know our initial concentration or the original concentration. What is the concentration after 5 hours? So we're asked to find the concentration after a time of 5 hours. Let's set it up. We need to find the concentration of sucrose at 5 hours. So I set up my unknown is on top, so we can call that x. The first thing I'm going to do is I'm going to simplify this right side. So I'm going to do negative 0.21 times 5. I got negative 1.05 for the right side. And that's equal to the natural log of, I'm going to call that x over 0.01. Next thing I want to do is get rid of that natural log. And if you look at your calculator, the opposite of the natural log is e raised to the x. So I'm going to get rid of natural log, but in order to do that, on the right side, I have to take e raised to the negative 1.05. So let's do that next. I'm going to just hit second ln to get that e raised to the, and then I'm going to do negative 1.05. So I got 0.3499, and that leaves me with the x over 0.01. To get x by itself, I need to multiply both sides by 0.01, and that will give me x is equal to 0.003499, and we want two significant figures, so I'm going to round that to 0.0035, and that is in moles per liter, or capital M. That would be my concentration after 5 hours. Let's do another practice. We've got hydrogen peroxide. It decomposes in a dilute sodium hydroxide solution in a first order reaction. Here's our H2O2 decomposing, and we're told that it's first order, so our rate is equal to K times the concentration of H2O2 raised to the first. We're told that K is 1.06 times 10 to the negative 3 inverse minutes. We want to know the fraction remaining after 100 minutes, so we're told T. What is the concentration of H2O2 after 100 minutes if the initial concentration is that? Let's set it up. All right, I set up our first order integrated rate law. I plugged in our K and our T. So I'm going to simplify the right side here and do our 1.06 times 10 to the negative 3 and times that by 100. And we know we need to take the negative of that. So negative 0.106. But our question wants the fraction. So we want to get rid of this natural log. And we know to get rid of the natural log, we need to do the opposite of the natural log, which is e raised to the x. So I'm going to get rid of that, but I got to do the same thing on this side. So e raised to the negative 1.06. Let's do that. So I'm going to do second natural log to get that. Negative 0.106. So my fraction would be 0.899. That satisfies the first part of the question. It wants the fraction remaining after 100, and this is our fraction remaining. But the second part says, what is the concentration if the initial concentration is 0.02? So I'm going to go a little bit further because we want to know the concentration after 100 minutes. So I'm going to write down that we want H2O2 concentration after time t, 100 minutes. And our initial or the original concentration given was 0.020. And that's going to be set equal to our 0.899. So I'm going to multiply both sides by 0.02. That'll cancel that out. So 0.899 times 0.02. And we should get, with three significant figures, 0.0180. Let's do one more for good measure. We have gaseous azomethane. It decomposes to ethane and nitrogen. So here's our azomethane. It's decomposing, and it is a first order reaction. We're told our K constant. We have a sample of it that's placed in a flask and heated for 150 seconds. So that's our time. What fraction of the initial sample remains after this time? And how long must it be heated so that 99% of the sample has decomposed? Let's see what we can set up here. All right, I set it up. Instead of writing the CH3N2 CH3, I just put X. Save a little bit of space here. So we weren't told our initial concentration or the concentration after a certain amount of time, which was 150 seconds, but we were told K and we were told the 150 seconds. And it wants to know what fraction of the initial sample remains. So I'm going to simplify the right side and do negative 3.6 times 10 to the negative fourth times it by 150 seconds, and I got on the right negative 0.054 is equal to the natural log of that fraction. So I'm going to simplify even further, and I'm going to do e raised to the natural log. And so I got to do it to the right side, e raised to the negative 0.054. And I'm going to get 0.947 would be my fraction remaining. And actually, after looking at our K, we were given two significant figures there and two significant figures there. So we would want to make this 0.95 for our fraction remaining, or 95%. For the second part, it wants to know how long a sample must be heated so that 99% of the sample has decomposed. Now, if 99% of the reaction is complete, that means that the remaining fraction that's left is 0.01, right? Because 99% is 0.99, and so we want the fraction of our remaining to be 0.01. So we can plug that in for the fraction and say the natural log of 0.01 is equal to negative KT. And we know K, so we can reduce even further. Natural log of 0.01 is equal to negative 3.6 times 10 to the negative fourth inverse seconds times time. We need to find how long the sample has to be heated. So to get T by itself, we just need to simplify this even further. The natural log of 0.01 is negative 4.605. To get T by itself, let's divide both sides by negative 3.6 times 10 to the negative fourth. We want to finish with two significant figures, so I'm going to make this 13000, so 13,000 seconds. Or we can convert this into minutes, but because it doesn't specify, I'm going to leave it as seconds.